Okay, so this is my first retrieval exercise, and just to help you out, because I'm feeling that way inclined, these are from P4, which is waves. So what I'd like you to do is pause the video and dig out your information on P4, on your waves topic. Now, there's a really good reason why I'm asking you to do this, is because when we get back, and you would naturally be doing this about now anyway, you would be doing your first half exam. So that would be half the topics. So you do all your exams, GCSE exams are in two halves, and you'd be doing your first one, first half, if you like, at the end of year 10. And it would include P1, 2, 3, 4, 5, and 6. And this is my way of jolting your memory into getting yourself organized so you have all of those in the same place. So find your P4, have a go at these. If you can't, then you've got a bit of work to do getting yourself organized. And that's the key point here, guys, getting organized. We shouldn't be chasing you because it's your responsibility. So pause the video and then I'll put the answers up on the next slide. Okay, so I'm on the next slide. I'm going to put the answers up and I'm just going to quickly scoot through them. If you're looking at your P4 notes and this equation isn't there, then that is an issue, because that's probably the only equation, that's not quite true, there are two equations in P4 that you need to know, and that's the main one. And this one applies in so many parts. Anytime we're talking about a wave, you need to know this frequency off the top of this equation off the top of your head. So using that, if we know that Wi-Fi, and this is the wavelength of Wi-Fi, so the frequency of Wi-Fi, so therefore what is the wavelength? I'm just going to quickly jot this down just so that we know if we want to find the wavelength, we need to rearrange. So velocity over frequency equals wavelength. The velocity of any wave in the electromagnetic spectrum, so Wi-Fi, is a microwave, which means it's moving at 3 times 10 to the power of 8 meters per second. Now that wouldn't necessarily be given to you. You might need to, it might be inferred, you might need to know it. And then the frequency, 2.4 gigahertz, which is times 10 to the power of 9. And if I put that in my calculator quickly, and if you haven't done this yourself, put it in the calculator just to double check my maths. So 3 times 10 to the power of 8 divided by 2.44 times 10 to the power of 9, and that comes out at 0.12. And remember, it's wavelength. A length is in meters in physics, or so we could say 12 centimeters or 0.12 meters. That's how big the wavelength of your Wi-Fi is, guys. So you can move around on your Wi-Fi and get good signal and bad signal depending whereabouts on the wave you are. But of course, those waves are bouncing all off the walls and different ones are reaching you at different times, which is why you don't have issues with your phone working and not working as you slide it across the desk. So if I press the next button, look at that, it's done the work for me. And question number 3, an ocean wave is passing underneath a rubber duck. What is its frequency? I did tell you there was one other equation you needed to know, and our frequency equals 1 over our time period. So in this instance, it would be 1 over how long does it take? It takes 3 seconds. Or we have 1/3, 0.33, and often is forgotten the unit for frequency. So there's a good chance to remind you, hertz. Capital H, small z for hertz. Okay, and this was a question I took directly out of GCSE exam a few years back, and it was linked to where does the duck move, up, down, forward, backwards, and the answer of course is just up and down. Waves don't move particles around, they just transfer energy into them. And what was the frequency, and most people panicked at that point, not remembering this equation. So 2 equations here, guys, that I'm circling. They need to be on your P4 sheet. If they're not, you're missing a trick. Well, we're going to get on with this lesson. We're going to look at good and bad electrical transfers. What makes one good, what makes one bad, and you can actually use exactly the same example for both, but I'll give you some realistic ones that would be in your everyday life. We're going to just have a look at a simple derived equation that's about calculating power. So some of the equations you've looked at already, just bring them together for a power equation. And I'm going to go into some detail about AC and DC. Not the band, we're talking about alternating current and direct current, but you'll probably see some very bad AC-DC jokes throughout this slide. I'm also going to have a quick look at cables in domestic appliances. And if you haven't seen Mr. Hurst's a video that he put out on wiring a plug, brilliant opportunity, guys, to see it being done for real in a video. There are lots of them on YouTube as well. I have a picture and I'm going to draw all over the picture, but if you want to see Mr. Hurst wiring a plug, and he's done quite a well produced version of it, it's one to definitely catch up with. Okay, so I promised you examples of good transfers of electrical energy, so I should clarify that we're talking about the electrical, and they might start as electrical before they go to good or bad. So the good example I thought I'd use is my old favourite, the hairdryer. Not that I use a hairdryer at all, but it is a good example of a good transfer because it's transferring electrical into kinetic. It's moving air. Now, whenever we do any sort of transfer, there's going to be some heat loss, okay? Because all those, whenever we're passing charge through or energy through all our free electrons in a circuit, they're going to be bouncing off each other. So there's going to be some thermal energy. Now, the good thing, what makes a good transfer in a hairdryer, mostly, is that actually we want some of that thermal energy. So we transfer electrical into kinetic and thermal. Now, there is a small amount of waste, and that's important to recognize here, but we would say mostly it's intentional. Mostly good transfers of energy are going on there. Now, one of the things that we do to achieve good transfers, well, we use larger wires, so we don't use very small wires on a hairdryer because there's lots of current going through. We want that path to be nice and easy. We don't want those collisions all starting to stack up on top of each other. We also want a high voltage. That's quite important. We use a lower voltage, we need higher current. So the higher the voltage, the less the current, the less collisions, etc. And we're basically recognizing that there is some thermal loss to the environment. But if you make your hairdryer well insulated, that might mitigate some of those problems. Okay, so bad examples. Now I'll give you a different one this time. We could use a hairdryer again and talk about some of that thermal loss, but I think we'd just be talking about the same thing twice. So let me use one that you're all probably familiar with. Charging your phone. Now, your phone, the purpose, the good energy transfer is electrical into chemical. You need to store that chemical energy in your battery. Now that's all well and good, but in this process here, this movement of energy, we get lots and lots of thermal energy transfer. Your phone gets hot when you plug it in and you're charging up. Most of you have told me that before. Most of you would have experienced this. If you don't believe me, go and plug your phone in, charge it up, feel the back of it. Where the battery touches the case, it's usually quite warm. And that's because the faster we do this transfer, the more of those collisions are taking place, and therefore we have more collisions, more thermal energy. And just to clarify, that is a bad example. Now, if those collisions, the faster we do it, the more collisions, the way to avoid actually heating your phone up while you're charging, not that you can actually do this, but if you were trying to save energy, you'd actually just slow the transfer down. Okay, because as something gets hotter, more and more collisions, so it actually starts doing that in terms of thermal loss. What we would prefer is something like a little bit flatter curve. So we want to slow the transfer down. Okay, so these are just two fairly everyday examples of good electrical transfers and bad electrical transfers. But again, we're just talking about moving between the two electrical stores. Okay guys, I've just moved on to the same, just cleared off that slide so I can show you the next bit, and because it appears down the bottom and I realised I had drawn all over that. How to calculate this. So when we want to know the energy transferred, so this is our energy in joules, we need to know the current for our I, we need to know the voltage for our V, and we need to know the time. Now, really, really important guys, that's in seconds, okay? So here's this equation. We're going to add that to our equation sheet, please. That little box that we've been making, and this is one of the last ones we'll be adding to it. So energy equals the current times the voltage times the time. And this is how your electricity meter works when we want to, and we don't touch on that again until P14, but we'll have a look at how energy is charged and how you pay for electricity, etc. But essentially, when you use a high current device for a long period of time, you're using more energy, therefore you pay more for it. And this is one of the fundamentals of understanding how you can save energy in your house. Either use it less or use less current when you make something more efficient or buy something more efficient. Okay, so now we need to put it into application. So these are examples of fairly typical questions that you're going to come across. So what I will do is I will let you pause this, and then I'm going to flick onto the next slide and I will take you through the answers. So please pause it now and I'll come back in about 10 seconds. Okay guys, so here we are at the answer slide. So hopefully you've had a crack at these, but if you haven't or you got stuck, I'm going to go through them one by one. So fast forward if you just want to see the answers because you've had a go at them, and if you're not sure, you can come back and see how I did it. So for number one, our easier one here, we're drawing 8.9 amps of current. Remember, this is current in the equation. This is our unit for current, amps. Okay, but we really just need to know the number, 8.9. Now our kettle is going to be plugged into our mains electricity, so we need to be able to remember that number. We're going to use 230 volts, and the time is in seconds. Now this is one of those lovely traps that they set for us. They give it to us in minutes, so to get it into seconds we need to times it by 60. 1 times 60 is 60. Then we take our equation, so we've got E equals I times V times T, and that's going to be 8.9 times 230 times 60, and if I get my calculator out, that will be 8.9 times 230 times 60 equals 122,820. What a lovely number that is, 122,820. Now of course I'll be looking to put a prefix in here, so divide it by 1,000, this is going to be in joules, but I want to make it into kilojoules, so that would be 122.82 kilojoules. Okay, or if I was doing it in standard form, because it's good practice, you wouldn't normally do this, but if you were asked to, we would then just do 1.23 times 10 to the 5. Yep, just double checking, counting my decimal places there. And standard form is obviously a great way of dealing with big numbers. Right, let's move on to the middle one. I'll underline it for those who are skipping through the video. If we've got two kettles in series, so let's assume we've got our voltage supply. There's kettle number 1, there's kettle number 2, and it goes all the way back around. Now I had 230 volts there, and I've got 0 volts there, even though I'm drawing this back to front. Let's fix that on the sheet. There we go, 230 volts on that side, 0 on this side, which means between these two I would have 115 volts, which means this kettle here has 115 volts, and this kettle here has 115 volts. So straight away, they don't have the ability to transfer as much energy. Okay, so if I have a look, how long does it take to boil? Okay, probably twice as long. Let's deal with one at a time. Oh, here you go. Question number 1, how many volts does each have? Well, we answered that, 115 volts each. And how long does it take to boil? Interesting. Okay, so if it took 1 minute, there we go, over here. I wonder where we're going to get that information from. How long? Well, if it's got half the voltage, it will take twice as long, roughly. But I think that was all that question was trying to get from you. Okay, so for the harder ones, anyone had a crack at the harder one? Good for you, because it's a great question. Entry required to increase water temperature is linear. So that means it's a straight line on a graph. So assuming the kettle from question 1 has 250 milliliters of water, how long would it take to boil a 25,000 litre swimming pool? So we just need to know what the comparison between. So we've got 25,000 divided by 0.25 times 60, because it took 60 seconds, and we should get a very long answer, because boiling a swimming pool would take a considerably large amount of time. 60. Okay, so I get an answer of 6 million seconds, which is not particularly useful. 10 to the power of 6 seconds. Okay, so if you want to take that a bit further, I imagine you would want to work it out into days, quite a few of them, hours, minutes, and seconds. And we do a good one of these later on in P15, as everyone gets to do a bit of practice at turning really large numbers of seconds into days, hours, minutes, and seconds. If you want to email me with the actual answer, feel free. Okay, so now we're looking at power for electricity, because we've dealt with power before. Okay, we've looked at force times distance is power, measuring the watts, and it doesn't matter what, excuse the pun, what we're measuring, what power, it is measured in watts. It's just energy being transferred, and it's energy being transferred in a given period of time. If we took time out of it, we would just be talking about work done. So this equation up here, I'll just underline it. So if you want to rewrite it slightly, power equals energy over time. Variable P. Power equals energy over time. And the question's asking which team used more power, and how do you know this? So if power is about energy being transferred in a given period of time, we want to know how much energy is being transferred and how long is the time. I'm going to let you pause the video, have a think about which one it is, see if you can show me the maths that would tell you which one is correct, and then when I unpause, and when you read unpause, I'll give it a gap of about 10 seconds, and then I'll show you quickly how I would work it out. Okay, so if you're back with us, okay, the first thing I've noticed is both teams have 1 million joules. Okay, the 80 litres of water is a bit of a red herring. We don't need to know anything about that yet, so let's put a cross through that. We can use that later. So what we're really interested in is the power, so the time. So team A. So A has 1 times 10 to the power of 6 joules divided by 45, and B, team B that is, has the same amount of energy, 10 times 6 divided by 75 seconds. So, which one's the higher number? Well, if I'm dividing by a small number, it must be team A. They're using more power. Now the answer, you could actually put in your calculator and find out, but we've proved it using some maths here. We've shown that team A, how much energy and time, and versus team B. So this is how we would demonstrate that we know something or why something is in physics. Now, if you had a go at the stretch exercise, so again, if you hadn't noticed it before, pause the video, have a crack at it, and I will stop talking for about 10 seconds, so when you're back in, I'll write the answer down for you. Okay, that's about 10 seconds, and you would have found the water would get about 3 degrees hotter, which is not really very much, but we are talking about 80 litres of water. Okay, so it does take a lot of energy to heat water up, which is why your kettle uses about 2,500 watts of power, so about 2,500 joules of energy per second go into your kettle, go into the water from the kettle. Okay, so power measured in watts per. What are our other equations for electrical power? Now we've already looked at these ones. So we've got PIV, which is our nice favourite one. We've got our derived equation. This one here is derived. And the question at the bottom is, does it matter what energy type is being transferred? Absolutely not. Energy is energy. We deal with it in joules, and we can move between energy stores. The more times we move, the more thermal loss we will probably have, but effectively we are just interested in total numbers here of joules, where we can use either volts, current, and time to work out power, or again up the top here, we're working out our power measured in watts. Okay guys, one of the topics we're going to look at now is AC versus DC. Now I've got a little bit of space over here because the C stands for current. They're both types of current. So we've got current in both of them, and on this side we have A, this side we have D. So the A is for alternating current, and the other side is direct current. Now, examples of alternating current, that's normal domestic supply. So what you have in your house is AC, and a good example of direct current would be a battery. Okay, and all we're talking about is the way the charge flows. So in alternating current, the charge will flow backwards and forwards. In a battery, the charge will just flow one way. Okay, now the key parts we need to know, and we'll start on AC. Now the reason why we use AC was actually we started using DC first, but we started using AC when we tried to scale up electricity production. We found that AC was much easier to produce, still is. It also comes with the added bonus of being able to step up to high voltage. The H in HV stands for high voltage, using transformers. Now we don't do transformers until much later on in year 11, so don't fret about transformers, just make sure you get this note down at this stage, and that will tie it together later. And the most important thing, and why it's in nice big red bold writing, it's at 230 volts at 50 Hertz. Now the 50 Hertz is because it is alternating. It's going backwards and forwards, backwards and forwards. Now if I use this edge of the table as a reference line, what that would look like if I could look at it as a wave, and we can use an oscilloscope to see this, okay, we would see the current going backwards and forwards, backwards and forwards. So up here it would be 230 volts, down here it would be minus 230 volts, but in the middle here where it's crossing over, it's 0 volts. In fact, there's no current or charge moving at all at these nodes, at these points as we cross the reference line. So what that really means in real world is that your lights that you have in your house right now are flickering. They're just flickering so fast you can't see it. Now some of you will have on your mobile phones high-speed cameras that are much better than my one. The more modern ones, I think it's up to about 600 frames per second. And I think at 600 frames per second you can just start to see the fact that the lights are flickering. So you'll see them go brighter, 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 darker, 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 then off, and then dark, bright, 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 and then maximum brightness, and then back down to off. And all that's happening is the current is flowing backwards and forwards, but every time it stops moving, there is no energy transfer, and the light is off. Now, what corresponds to that is DC. Now, there are some big advantages with DC that you don't get in AC. Well, the first one is constant voltage. You don't get this up and down. Okay, and that could be a real problem with electronics and meshing different parts of buildings together, because if these waves don't line up between two pieces of equipment, you can do some really big damage. So DC does have that advantage of being constant voltage. Big negatives though, high loss. And if we'd stuck with DC as was originally planned by Thomas Edison and all of his patents, we'd all have a power station in every 20 or 30 houses. Not something that would have been particularly wanted or desired. Now, one of the ways of overcoming this high loss is to get rid of low voltages and go to high voltages. So we do have some high voltage DC now that we bring in from overseas. It comes across a channel from Holland, so when we buy in electricity from overseas, but it's more in the minority than the majority. It is most certainly more complex to produce high current loads in DC. That being said, the reason it is easy to produce is because of the way we spin our generators. So our turbines in power stations are pushed via steam. It doesn't matter how the steam is produced. The turbine spins, and a natural production of a turbine, a generator on a turbine, is just as it spins, is to produce a current that looks like this. Obviously, that is, as we've just had a look down the bottom, AC. Okay, so those are our two big things here. Now, I did say there would be one easy question in the quiz this week, and it's going to be, what is Mr. Gregson's favourite band? And the answer is AC/DC. And I'm going to put down some ridiculous answers as well, but if you've got it right first time, it means I know you've watched this PowerPoint. So thanks for watching. Remember, AC/DC is the correct answer for the first question. Okay, so we're going to move on to understanding why we have the kind of wires we have in a wall. Now, most people will attribute the live, neutral, and earth, which is written up the top here, on neutral and earth, to plugs. But actually, what you'll find if you ever get to do any electrical work is that all the wires in the walls that are around us at school, in the cabling, in the boxes, all have 3 wires, and these are what the 3 wires are. Now, the first one now is often coloured brown in a domestic household. It does come in other flavours depending on the need or where it is. In certain industrial buildings, it can be multiple different colours. But live is typically brown, so if you're ever wiring a plug, you're looking for the brown one for live. Neutral is our blue, and our last one is our earth, and that will be green and yellow striped. Now, just very, very quickly, you need to have this information written down on your revision notes, but the live provides our potential difference, the ability to do work. So our potential difference, it's the one that will hurt you if you touch it. Our neutral is the return path. Okay, so if we thought about, I'll try and draw it better this time, and here's our light bulb. We need to have our live in this side, and to get it back to here, now this isn't a proper circuit, this is a made up one, we need to have a neutral, otherwise this bit doesn't exist and therefore nothing happens. So our live is our potential difference, our neutral is the path back. Now the last one is the earth. Now the earth won't appear, and if you watch Mr. Hurst's video, the earth doesn't appear in every appliance. It's more to do with appliances that are higher risk. So things like toasters will have an earth because they get hot, they get wires wear out, and it's basically a safety feature. Now, occasionally, if we might have some wires going through a metal plate, and if this metal plate, that I'm trying to draw very badly, moves backwards and forwards, the wire starts to rub, and some of the inside of the wire, the insulation was worn through, and it starts touching our metal plate, which means that this metal plate now is live. This is bad, because if you were the next person to pick that toaster up and touch that, the electricity would go through you back into the ground. You would complete the circuit, so the electricity would flow through you. To avoid that, which is obviously a good thing to avoid, we attach over here an earth wire, so that in the event that that plate becomes live, our current will flow straight down to earth. Now normally the current will be so high that our little circuit breakers that we have in our houses would drop down straight away, so it would trip the circuit breakers. Or a thing we have, an RCD or residual current device, that basically says there's current that shouldn't be there or doing something it shouldn't be doing and trips off. We don't need to learn about RCDs at GCSE, but handy to know why you do have them in your house. It's to stop you overloading the wires, so there's not too much current going through the wires, and the RCD is often a great way of saving someone's life. They should trip out faster than somebody's heartbeat. So in the time it takes your heart to beat, the RCD should trip out, so that if you were unfortunate to touch something that was live, you're unlikely to even know it occurred. So there are the 3 types of wires, and on the next slide we'll go through them. Okay, so like I said earlier, if you want to watch it actually being wired in the video, Mr. Hurst's video, I haven't got a link up here, but essentially you can make out that the brown wire, our live wire, comes out of the plug, goes through, now this is quite important, a fuse. Now we've talked about fuses already, and size of fuses, this is where the fuse is. Now, it might not be the only fuse, but almost every electrical appliance that plugs into the domestic will have a fuse. They will be different sizes depending on, they might be 1 amp, 2 amp, 3 amp, 5 amp, typical sizes of appliances. Excuse me. Now this part here that the fuse is attached to is what you would see on the other side of the plug as one of the prongs sticking out. So if you ever wondered which one is live, as you're looking at the socket, so if you look at a socket like so, this one is live, this one is neutral. Okay, so the blue wire, now that doesn't go through anything, it just goes straight into the metal plug on the other side, and our earth, same. So we end up with, if you're looking at a socket, the one on the right is the live. Not that you should stick anything in any of them anyway, but what you'll notice in the UK we have one of the safest plug designs because there will be a door over the top of the live. You can't just stick something straight in, and that door doesn't open until the much longer earth plug gets pushed in first. So you'll notice if you look at a plug, the earth will be slightly longer. So as that pushes in, that door lifts up out of the way, exposing the live. So you shouldn't have the live ever exposed to somebody putting something in there, like pens and forks and all sorts of things that children, young children in particular, will stick into power points. So there you go, guys. There's quite a lot of information being thrown at you there. So we've looked at good, bad electrical transfers, demonstrating calculating power, and AC, DC, and recalling all three types of cables in a domestic appliance. You need to take down those notes on AC, DC, and particularly around wiring of plugs and cables in domestic appliances. There'll be 10 questions in the quiz, and they will all revolve around your ability to demonstrate calculating power and the key points from this slide.